what everybody was asked to do was to do a little test to see how well they could identify phishing websites. And then they had to take a 15-minute break, and then they took another test. And during the 15-minute break, the experimental group got to read these websites that teach you how to avoid phishing attacks. And the control group just got to play solitaire. So we found out that playing solitaire does not teach you how to protect yourself. Not a surprise. But the more surprising result was we found that the people who read the training materials actually learned something. That was somewhat surprising given all the people who don't seem to know how to protect themselves and how readily available these training materials are. So is it that simple? We just need to get people to read these things that are already there and problem solved? Well, unfortunately, no. So here are the problems that we found. So the first problem is that people normally don't go and read those training materials. The reason the people in our study read them is we paid them $10. It's a good incentive, right? And we were there watching them to make sure they did it, right? But normally people don't seek out these materials and don't actually do it. There are some companies that have tried the strategy of, well, let's email out these materials to our own employees or to our customers. And people don't read those either. We did a different study where we tested that, and we proved pretty conclusively that nobody reads those kinds of emails. There's also a problem with some of the training materials themselves in that they do tend to make people just kind of paranoid about everything. And while in our testing we found that they were better able to identify phishing emails, they also had a lot more false positives in identifying or mistaking legitimate emails for phishing. We need a solution that is a way of actually getting people to the training materials and convincing them to actually pay attention. What we're looking for is what we call a teachable moment, a point where people are actually going to want to learn, to be receptive to learning, and to find the learning relevant to what they're doing. We developed a system called PhishGuru, which I'm going to tell you about, that takes advantage of this teachable moment. The second thing that we want to do is we want to make training fun so that people will enjoy it. They'll want to finish it because it's actually fun. They're not going to just look at it for 30 seconds and move on. And they might even suggest to their friends that they do it too because they had such a good time doing it. And to that end, we developed a game to teach people about phishing. And I'll tell you about that as well.
We do everything the same, but now in addition to watching out for these secure links, we also watch out for favicon requests. And if we see a favicon request for a URL that we've stripped, for instance, a favicon request for a URL that should be SSL, should be secure, we'll send back a favicon of our choosing instead, right? And so what should the favicon be? You guessed it, the lock icon. So here's another version. Here's the secure site. This is Gmail's login. This is the secure version. This is the strip version. It's cheesy, but you get the little lock icon up in the favicon thing, and people like the lock icon, and it's there. So maybe people won't know the difference. So they're doing pretty good. We avoided the negative feedback of death. If we get this, we're done at all costs. We can do a subtle man in the middle via HTTP. And if we want, we can throw in the little padlock in the favicon thing. Some sites provide no visible difference. Here is this. This is the intact version of Wachobia's login page. This is the strip version. Show it to you again. Original, stripped. Original, stripped. And since what we're after are the login credentials, essentially, this tool has a mode where once it sees a secure post, it just ducks out. So once we get the secure post from this login page, the tool actually ducks out of the man-in-the-middle process and lets the browser upgrade itself to SSL. So as a user, there's literally no way to know that this has happened to you. You log in, and the next thing that you see is an encrypted site. Sometimes the sites themselves confuse us, right? Here's PayPal's login, right? They've got all this stuff on their site. They've got a little lock icon, all these things that are trying to tell us that this is secure, but they don't know. How do they know that this is a secure site? They don't know what's happened to them between the client and them. Here's E-Trade's login. Again, they've got their own little secure login button. They've even embedded the lock icon into the graphic itself. I mean, they've gone to the next level, right? So you look at the site. Is this the secure version or the stripped version? It's the stripped version. But there's really no way to know unless you're, I guess if you use the site a lot and you're a really attentive person, you would know. But just looking at the site, this pattern is common enough where they've got their own imagery, their own secure imagery in here. This could be the normal version of the site. There's no way to know. So there are a few gotchas in this process, right?
Let me start with an example that's pretty straightforward. I imagine everybody here remembers the Enron scandals and the fraud that went on. One part of the fraud had to do with Enron trying to book more revenue and more income than it was entitled to by selling a barge. That's right, it was actually a maritime vessel. And they sold it to Merrill Lynch. Now, some of you may remember this incident, some of you may not. And the way they sold it to Merrill Lynch was to say, well, we will sell this to you, Merrill Lynch, so that we will be able to book a gain. But Merrill Lynch really had no interest in buying the barge. So what Enron's executives said, well, you know what, we'll sell it to you, but then we'll buy it back within 90 days. Now, there's probably nobody here that studies accounting. I'm an accountant and a CPA. If I sell you something with an agreement to buy it back, it's not a sale. And if the accountants had known that the sale of that barge was accompanied by a repurchase agreement, they would not have allowed the sale to be booked as income. But do you think Merrill Lynch was going to do a deal like this without something written? Of course not. It's way too big of a deal, way too important. And a memo was written by one of the people in Enron that laid out the entire scheme, showed how it was going to work, that there would be a sale, what the vessel was, how it would be sold, what the transaction would be, when it would be booked, what part of the business would receive the income, how it would be purchased back. And it was a great memo. Some people printed it. And during the criminal investigation after Enron failed, people were given copies of this memo in paper form. And the question is, all right, that's the paper form. Where's the electronic version? Became known as the Immaculate Conception Memo because nobody who handled it said that they wrote it, saw it, read it, remembered viewing kind of, where they saved it. And we couldn't find it in the Enron records. But we did go to Merrill Lynch and able to use a couple of techniques, including hash values and other things, to search within the servers of Merrill Lynch to see if we could find this memo. Now remember, we're already into a form of manipulation because somebody knows this is an electronic computer file, but they don't want anybody to find it. And we found it inside the home directory of one of the executives at Merrill Lynch who was a defendant in the criminal case. He was on trial, and the very fact that this document was inside his home directory, and I think it was actually a copy of a home directory, was devastatingly bad for him at trial. It showed a real sort of state of mind and intention.
We've run some statistics, and going through the whole experiment, you can see that traditional approach, really fails at 30 degrees. 15 degrees is able to do something 70%. With a 3D approach, we're basically, getting about 97% across 15 and 30 degrees. So we're collecting a new data set, with a whole complete 3D creating facial. We also have cameras to capture 2D images, so we can do benchmarking as we go to 45 degrees, 60 degrees, and beyond. And that will be able to show our findings there. So as we did that, I said, I called my student one night, and well, I shouldn't say the microphone, but it was 1 a.m., 2 a.m., had a brainstorm, and of course they're working in the lab too, and I was up somewhere giving a talk, and that's when best ideas come up. So he said, you know what, let's try this on an actual episode. Let's get an episode of Seinfeld, since that's what my students really love. At least Utsav loved that. So this is actually matching them. Again, each frame was actually independently matched. There's no temporal tracking. There's no temporal information about, who was there at one frame. There's no scene change. None of that. Each frame was identified independent of each other. Now, at some point, you will see Jerry and Elaine, some confusion. You will see Jerry sometimes call Elaine and vice versa. And if you look at just the facial crop at that low resolution of, 30 by 30 pixels, their smile and nose does actually sort of resemble each other. And that's what's going on. With the compression artifact in such low resolution, it does confuse. Now again, we're using the simplest, dumbest matcher possible, right? Normalized correlation. X transpose Y, assuming, of course, making the X and Y unit norm. So we've also made a real-time demo. Our latest one includes pose estimation, so we're not doing the whole thing. So right now I'm basically giving an off-angle face, and it's going through all images in the database of the people in my lab. So that's Ramsey, and it's basically looking through everyone and trying to match who I am. So that's actually a real-time capture.
The second idea is the compositional security principle itself. So how do we recall the question? Our goal is to prove that S1 composed with S2 is secure based on properties of S1 and S2 that are provable separately. And the idea here is what we call rely guarantee in the presence of interface-confined adversaries. So at a very high level, the idea is that in proving the security of the composed system S1 and S2, each will rely on the properties that they're provably guaranteed to satisfy in the presence of interface-confined adversaries. So both S1 and S2 will make some assumptions about how the other guy will act, and we can separately show that each will respect each other's assumptions and guarantees. So that may sound a little abstract, so let me give you a simple example of how this idea might apply to protecting a secret in a group, right? So suppose that there is some secret information that you and I want to share, and we don't want anyone else to know that secret. Now, to maintain that property, I will have to exchange information, exchange messages containing that secret in a way that from those messages, only you can acquire the secret, and then you have to act in the same way. So one example of something like this shows up in protocols like Kerberos, which protect secrets, which ensure that secrets are only shared by 2 or 3 people. And in network protocol case, the way that is achieved is by using encryption. So every occurrence of the message containing the secret that is sent out on the network will always be under encryption with a key that is only known to the group to which we want to whom we want to constrain that secret. And then actions taken by parties in the group will always locally preserve this global property. So let's assume, to make things more concrete, let's assume that there is some predicate like safe network or something that keeps track of that is true if the secret is only known to the 3 of us, the 3 people who should know the secret. And then under the assumption that safe network is preserved, if we locally only perform actions like sending out the secret encrypted with keys that are only known to the 3 of us, then under this assumption, each of us will act in a way that will continue to preserve this secret, right? So that is what I mean when I say that S1 and S2 each rely on these properties from each other that can, in fact, be provably guaranteed, even in the presence of adversaries that are confined to certain interfaces.
This was done about a month ago. I was trying to get some CyLab. So I'm running on Google, no prescription CyLab. It's a little bit small, but the third link here is www.something.cs.umass.edu. I didn't know that the University of Massachusetts actually sold CyLab, but apparently they do. Now you will notice that the URL is actually completely different. So what happened? Well, let's cut and paste that URL. I mean, is the site have completely compromised? Not really. I cut and paste this URL, and I go to the website directly as if I wasn't coming from Google. And this is actually a networking and distributed systems research group, who obviously needs to hire a systems administrator. This is not limited to the query that I just ran. I was not very inspired, so I was really looking for CyLab, but you can try it with Percocet, Viagra, anything. And you will see that some sites sometimes are marked as compromised by Google. Google tells you something may be fishy. Yeah, I mean, it's cgi.media.mit.edu. And that is why you're at Carnegie Mellon and not at MIT. You go there, and you've got those 3 handsome doctors telling you that they can solve all of your problems. Now, if you go to the site directly, and I'm going to interrupt this because we don't have so much time, but it doesn't do anything. It's actually a repository for scripts that the Media Lab at MIT is using. So what's going on here? I mean, it's somewhat weird that those sites have a different behavior depending on whether or not you're coming from Google. Well, what happens is that there are 3 things that happen. First, the attackers has managed indeed to compromise those sites. And they've been able to do so in a way that leads them to be present in the search engine results. Now, if you click on one of those infected results, cgi.media.mit.edu, which I think has been cleaned up, by the way, since I did that experiment, you're going to land, indeed, at cgi.media.mit.edu, but your request is going to be intercepted by a small piece of software that the attacker has injected. And if it notices that you're coming from Google with, in the referrer terms, you have something like Viagra or Vicodin or whatever, it's going to send you to another website by issuing an HTTP 302 redirect. After one or more of those 302 redirections, you're going to land on the final pharmacy store. Now, if you go directly to the website, not from Google, so your HTTP referrer terms do not include Viagra, they do not include Vicodin, the piece of code is going to look at this and say, OK, that's a legitimate request, and just displaying the normal contents of the website. The reason why they do this is so that those websites cannot be traced easily as being compromised. Unless you run those queries, you don't see that you've been hacked. There's nothing that's particularly obvious about it.